Hi, this is Physical World, lecture 29, and it covers chapter 19, and we'll mostly talk about circuits. So today I'm going to introduce something new again from chapter 19, but we might not cover all of this chapter. And the good news is that we will not have too many things to cover before exam 5. So we will cover chapter 19 and 20 only, and we will break it down into a few lessons. I don't want to rush through things, and I want to make sure some students ask to do more examples, and I will make sure to do that. And other students said they liked it, how I gave you real life examples as well, not just problems. So I will try to do that as well. But then again, I'm in danger of running out of time. So what I will do is I will just try my best not to rush through it and just break it into more lectures, this material that we have. And I don't want to end up skipping any of the topics, but if we have to, we will do so. So I will make sure we cover everything thoroughly. And it's only 2 chapters to cover before exam 5. And this is good news because you will have to, there's only this much you would have to learn. And those students who want to improve their grades, it's an opportunity for them to do so, as long as you stay on track again and stay on top of it. So one more thing I wanted to say is on homework, I want to come up with something new. So every time you have a homework, I will make sure to have a video solution of this homework as well, so that if you are guessing on homework just to get grades and you happen to guess it, I don't want you to end up believing that you know it. So unless you are confident, 100% confident you understand this question really well, you do need to check solution for that. Either contact me, email me, or through Zoom, make appointment, or whenever we have a Zoom meeting schedule, see me then to ask homework questions, or check recordings of homeworks as well. So they will be available as well for you to double check that you understand homework solution. Also, today we are covering something that's more mathematically involved. Especially one of the things we are covering, it involves lots of algebraic manipulation as well and arithmetic calculations. So what I would recommend is try to stay focused, but at the same time, let me know if you are confused. I would say question 4 on homework is towards the difficult side rather than easy. So what I will do is if I bring a difficult question at the exam, for example, per each difficult question, I will also bring a really easy one as well. So I'm trying to balance exams in such a way that we have equal amount of difficult and easy questions. And then the rest of the questions would be around medium level of difficulty. So let me know if you're confused about any of this, and I will give you even more help. So we are covering today electrical energy and power, and how to figure out how much you have to pay for your electricity. And we might talk about fuses and maybe what happens if you have more than one receiver and how many ways you could have that in the circuit. So before moving on to that, I quickly want to remind you what we covered last time. I feel like I didn't give you enough, just one question is not enough, so I will give you 2 more questions, solutions to those, and maybe give it to you as a homework as well before the exam. So here it is, the formula we covered, the definition of current really. What is current? Current is this formula I'm talking about. So current is amount of charge per time that passes through a point. So here's another way of writing it. Current is charge per time. In some questions you might be given amount of charge in coulombs. Question 2, for example, in which you just have to plug those numbers into the formula, and it's easy because you just plug in number of coulombs divided by number of seconds, and that's the current. What if we have number of particles given instead? Then we would have to know charge per particle instead. So you would have to do one extra step. So I will consider both examples and then give you homework on that to practice, so that you can get practice too. So let's start with the second example because that's easier. So it's given that 5 coulombs of charge, so charge equals 5 coulomb, passes through a point in 20 seconds. So time equals 20 seconds. What is the current in the point through this point? Well, to find that, what we need to do, so current is question mark. What we need to do is think about which equation to use. At the exam, you would have to consider all of the equations you have. But here we have definition of current really, charge per time, charge moving through a point per unit some time interval. So I'm going to use that formula. So charge is 5 coulombs, time is 20 seconds, so it's a quarter or 0.25 amps, and that's the amount of current we have. Now I want to do this first question here, which is a bit more difficult because you don't just plug in numbers in the formula, but total charge is something you need to figure out. So each electron has a charge of 1.6 10 to the minus 19 coulombs. So charge per each electron is given. And we have number of electrons, so let me call it n, for example. 200,000 electrons. And we have time given as well. To find total current, we need to find total charge, and time is given. So total charge is something we need to find. If we know that each electron's charge is given and we have so many electrons, how would you find total charge? Well, if you had 2 electrons, you would double that charge, right? If you had 3 electrons, you would have triple that charge. So n electrons means n times that amount of charge. So what I'm going to do is say that Q total equals number of electrons multiplied by charge of each electron. So that's 200,000 multiplied by 1.6, 10 to the minus 19 coulombs. So that will be the total charge. And I need to divide all of this by time, right? So let me figure out what that is on a calculator. Well, actually, I don't need a calculator. This will be 2 times 1.6 is 3.2. And then 10 to the minus 19 multiplied by 1, 2, 3, 4, 5. It will be 10 to the minus 15. Oh, 14 even. So yeah, you can double check if I'm right. And we are going to divide all of this by time, which is 2 times 10 to the minus 4, okay, 0.0002 seconds. So that will give me 3.2 divided by 2 is 1.6 again. So something like 1.6, this is in coulombs, 1.6 10 to the power of 3, 4, so negative 10. And that will be in amperes. So that's how you find current through a point, given even number of charges and amount of charge and charge per each particle, or just total charge. Those would be towards easy side of the question. I want to say they are quite easy. And this one here is medium level of difficulty because you have to do this extra step, but it's not too bad. So let's move on to something new. It's not really new because in one of the slides I remember mentioning what power is. Power is the rate at which you do work. So the more work you do per time, the more powerful it is. The device, for example, a powerful horse would carry more stuff per unit of time. For example, it would carry a bigger box, heavier box, do more work in the same amount of time. Or if something is powerful, it consumes more energy as well. So think of it this way: if you have energy and work are interchangeable, really, we talked about this at some point. So work is change in potential energy. Don't worry about it too much now, but all I'm saying is you could think of power as amount of energy consumed per time as well. So work done per time, or an amount of energy transferred per time, or amount of energy consumed per time, per how fast energy consumption happens. That's how you can think of power. Now, if power is that, power is amount of energy per time, then we need to come up with a different versions of energy per time. We can't think, so electrical power is also defined as current times voltage, and I will explain that in a second. So what we have here is current and voltage, right? But current is charge per time. We talked about it on a previous slide just now. So charge per time, how much charge flows through a point in a given time is what current is really. And voltage was energy per each charge. So how much energy is applied to one charge to move it, right? Energy required to move each charge, for example, in a circuit. That's what voltage is. So what we have here is charge per time, energy per charge. And you could think of it this way: charge cancels and we have energy per time. So it should make sense, but I want to even talk more about it, give you intuition behind why power is current times voltage. Think of it this way: if I connect a device to an electrical circuit, then a light bulb, for example, the more current flows through it, the more energy it consumes. So you will have to pay bigger electricity bill, for example. Or if you leave it on for longer, then I guess as well, you would have to pay more. And if voltage is higher, if you connect it to a battery that's higher voltage battery versus lower voltage battery, you would see that higher one would be brighter. So this is coming from somewhere, right? This brightness. It uses energy to give you more brightness. So more brightness means more energy consumption. So it all should make sense qualitatively why power depends on current and voltage. But we will focus next. We will focus more about quantitative example. And before we talk about that, I quickly want to give you a few more things. So this is just another version of this formula. So this formula here is symbolically given to you, and this is just the same thing but verbally given. Power equals current times voltage, in case you forget what is I and V. At the exam, you can use whichever you want, of course, and units of power would be watts. We talked about it, and we said that it's joules per second. Last time we defined power a few weeks ago, but this time I'm going to tell you it's amperes per times volts, but they will end up being the same units anyway. Joules per second is the same as amperes per volts if you break them down. And we know that energy consumption rate can be expressed. Let me erase all of this. So energy, we want to find energy now. Remember, so power is energy per consumption per time, or work per time. So if I rearrange this equation, I will get energy equals power times time, right? Because I multiplied each side by t. So this is what I'm giving you here. Energy equals power times time. This is coming from power equals energy per time. Multiply each side by t, and you will get this equation. And now, if I replace power, this one here, with current times voltage, so that's what I did here, current times voltage, you will have a new formula for energy. So energy equals current times voltage times time. So this quantity here really is power. So power, all I did is use the previous equation and replaced it with current and voltage, product of those. So if I give you current, voltage, and time, you should be able to figure out the power, or to figure out energy. And if I give you, for example, other quantities, you should be able to manipulate those equations. So let me give you examples on that. At home, you know that you have, in the mains, we have 120 volts of alternating current, and that's a standard. So if you go to a different country or different place, you might have a different standard. So for example, in some countries it's 110 volts or 240 volts. Here we are using 120 volts. So if you go to somewhere else, you would have to probably use a transformer or something but we will talk about that some other time. So basically, all you have to know is in the mains we have 120 volts. And if voltage is 120 volts, then if we have half amperes, so amount of current is half amps, if you multiply those two, half multiplied by 120 is 60 watts. So yeah, 60 watt light bulb would draw a current of 0.5 amps. So if I ask you how much current does 80 watts light bulb draw, well, you can use again, voltage is fixed and power is given. It's normally written on the light bulb, so you can figure out how much current it draws. So for example, 100 watt light bulb. So if the wattage of light bulb is power is 100 watts, how much current flows through that? If I have 120 volts, so current from there equals, I'm just giving you different variations of the type of questions you could have really. Power divided by voltage, which is 120 divided by 12. So about 0.8 amps is how much current flows through that. Here I want to talk about your electricity bills and consumption of power. So when you are paying electricity bills, what you are paying is the amount of energy you consumed. So when you get electricity, your devices you have at home, for example, microwave, refrigerator, light bulb, all of those, microwave oven and other things that operate on electricity, they would consume electrical energy. They would convert it to something else, another kind of energy that is useful. So light bulb would convert the electrical energy into light energy. That's about 10% at most. But also there is 90% of thermal energy produced, which we don't want, but there is nothing we can do about it. So lots of energy is wasted and used as well. So every time you operate something electronical and connect it to the mains, you are using the electricity, electrical energy delivered to your house. And those devices convert it to some useful work or something that we need to different types of energies, right? So you have to pay for that energy. If you noticed, when you get the bill, you always have the units kilowatt hours or watt hours. So what does it mean? Why kilowatt hours? It sounds like energy units should be in joules, right? But then we talked about how it can be measured, energy can be measured in electron volts and other. So there's lots of ways to give you energy units. And these kilowatt hours units, I will try to explain where it's coming from. So remember how power is energy per time or work per time. So joules per second, right? But now if I rearrange this and I solve for energy, then on the previous slide we saw energy equals power times time. So energy equals power times time. And here it is, energy equals power times time, this equation here I'm talking about. So powers, units of power multiplied by units of time should give you energy units. Units of power is kilowatt or watt, and units of time is either seconds or hours. So we don't use seconds and we don't use watts, but kilowatts, which is 1000 watts, and hours, which is 3600 seconds, because we get nice numbers at the end. So we don't want to be working with really huge or small numbers, reasonable numbers. So that's why we use kilowatt hours. So just keep in mind, kilo means 1000. So kilowatt means 1000 watts. So whenever I want to convert, for example, 3000 watts to kilowatts, I divide by 1000, so it will be 3 kilowatts. So that's simple. And time, try to have it in hours in our problem so that it's easier to work with those. Now, if electricity costs 15 cents per each kilowatt hour, so what you are paying is amount of kilowatt hours you consume. Remember I said you pay for energy you use, so you are using this energy which has units kilowatt hours, right? Kilowatt hours is energy units, remember. So if I consume 1 kilowatt hour, I pay 15 cents because each kilowatt hour costs 15 cents. If I consume 2 kilowatt hours of energy, I pay 30 cents and so on. So how much would I pay if I consume 10 kilowatt hours of energy? Well, 10 times 15 cents, which is 150 cents, or $1.50, for example. So, for example, let me give you several examples and then we will go do lots of problems on that. So 2000 watts would be, well, remember we need to convert it to kilowatts first before we start doing anything else. So 2000, because the unit is kilowatt hours. It's a funny way of giving units, but that's how it works. So let's convert it first. Because the price is given per kilowatt hours, that's why we have to have power in kilowatts rather than watts. So 2000 watts is 2 kilowatts. And time is 4 hours. So power equals 2 kilowatts. Time is 4 hours. So how much energy? Energy is power times time. So 2 times 4 is 8 kilowatt hours. So 8 kilowatt hours is the amount of energy we have. Now, if each kilowatt hour costs 15 cents, right here, then 8 kilowatt hours would be 120 cents, which we can convert it to dollars if you like. So $1.20. Yeah, I should really write here 20. $1.20. So you hopefully see how it works. You figure out how many kilowatt hours you consume and then multiply it by the cost of each kilowatt hour, and that's how much you have to pay. If power is given in watts, you need to convert it to kilowatts. And then time, it's preferable to have it in hours because the cost is given for each kilowatt hour. That's why. In this question, we have a refrigerator that has a power rating of 500 watts or 0.5 kilowatts. And you can see that refrigerator is less powerful than the iron, right? So do you think I have to pay more or less at the end of the month, for example? It's misleading because you would think that it's less powerful, 4 times less powerful. 2000 versus 500, 4 times less. So 4 times less power, but remember, refrigerator is always on. And the iron you occasionally use several hours per month, suppose. Some people don't even use iron. So at the end of the month, it's time that matters. So because you are using a refrigerator for much longer time, it will you will end up paying much more due to consumption of energy by refrigerator rather than by iron. So all electrical devices normally have something like that written to it, and if it would give you an idea about energy, how much energy it will consume, I guess. So it says here that its power rating is 55 watts. So its voltage it operates is 120 volts, which we have in the mains. If it was different voltage, I would have to use an adapter or something to make it usable for my different type of voltage source. So this works at 115 alternating current volts, 2 amps, 60 hertz. So normally in the mains we have 60 hertz frequency and of oscillation of current because we have alternate current, remember? So where is the power rating? We can find power if you want because it would be 115 multiplied by 2, right? Voltage times current. So voltage times current, that's what I'm doing. So you have 230 watts. In this one, you have 230 watts is the power rating for this one. So all the devices would normally have a power rating on it, and you can easily get more information out of it once you know what it means, really. And again, one more example. Suppose a toaster is given to operate, again, 120 volts, because that's what we have in the mains, alternating current of 120 volts voltage. And it consumes 900 watts. So that's a power rating. And we have another device which is operating at 6 amperes and 120 volt circuit. So which one consumes more energy in 2 hours? That was the question. 120 volts is given and 900 watts. So we don't really need this information at this moment because we can just use power times time. Time is 2 hours, power is 900 watts, but let's write it in kilowatts if you like. So 0.9 kilowatts multiplied by 2 hours is 1.8 kilowatt hour is the amount of energy that's used by a toaster if it works continuously for 2 hours. Now let's find energy consumed by, what was another device? Vacuum cleaner. And now we need to find power because it's not given. So power is current times voltage. On the previous page we found, right? So we have 6 times 12, so 720 watts. So that would give me 0.72 kilowatts. And if I have 0.072 kilowatts and it's on for 2 hours, total energy consumed would be 2 times that, right? So it would be 1.44 kilowatt hour. So from here you can see that the first one consumes more energy than the other one. But if then the question is, how about weekly consumption if I spend 14 minutes per week toasting bread and 30 minutes per week vacuuming? So now suppose I don't use this as much as this. So this one only for 14 minutes and this one for longer, 30 minutes, half an hour. Then I guess total energy bill would be bigger due to the second one, right? Due to vacuuming rather than toasting bread. So although for 2 hours continuous use, the first one uses more energy, in the long run, I don't use this device as often, so I would end up paying more for the second device. But let's do this example now, and it has a solution here as well. So this is how I would give you the cost per kilowatt hour. So 15 cents per kilowatt hour means that every kilowatt hour costs 15 cents. So we have the cost of 1 kilowatt hour of energy. Now, what does it cost to operate this power this hair dryer, which is rated at 1200 watts, and I'm operating it for 2 hours. Again, what you want to do is convert this to kilowatts, 1.2 kilowatts, and 2 hours times it by time, and we get 2.4 kilowatt hour. So this is total energy consumed by each in 2 hours. So how much does it cost? Well, multiply this by cost per each kilowatt hour. So if I have cost for 1 kilowatt hour and I want to find how much do I pay for 2.5, almost 2.4 kilowatt hours, I just multiply cost per each by number of kilowatt hours, right? So what I'm going to do, let me write this one in detail. So 2.4 kilowatt hour multiplied by 15 cents per kilowatt hour. Can you see how kilowatt hours cancel if you want to do it this way? And you have 2.4 times 15, which is 36. So 36. And units will be cents, right? So 36 cents is how much it costs you to operate hairdryer for 2 hours approximately. So you get an idea how it's done. Those kind of questions are not easy because you have to do so many conversions, but it's not too bad. I think if you practice enough of those, you should be able to do your homework question 4 on that. I will do 4 examples on that and then move on to something different. So suppose now we have a lamp that is operating at 100 watts continuously for 1 week. So can you see how time is not given in hours? So you have to get it to hours first. And the cost per kilowatt hour again is given. So how much does each kilowatt hour cost? This 1 kilowatt hour energy costs 15 cents. And we have to show that total cost will be $2.52. So the way to do this question is, again, first thing you want to do is find power in kilowatt hours. So that would be 0.1 kilowatt. In kilowatts, I mean. So now find time in hours. So 1 week, how many hours would that be? So this is power. And time would be, 1 week is 7 days, right? Days. But 7 days is 7 times 24 hours. And let's do that. 7 times 24 is 168 hours. So we have 168 hours and this much power, 0.1 kilowatt, and we are ready to find total energy. Energy in this strange units, right? Energy in kilowatt hours would be 0.1 multiplied by 168 hours, which will give me 16.8 kilowatt hours. And this is the right unit now. I'm almost there. Now, if I know that 1 kilowatt hour costs 15 cents, if I had 2 kilowatt hours, I would pay 30 cents. 3 kilowatt hours, I would pay 3 times as much, and so on. So if I have 16.8 kilowatt hours, total cost will be 16.8 kilowatt hours multiplied by cost of each, 15 cents per kilowatt hour. So I will get 16.8 multiplied by 15 will be 252 cents. And I could convert it to dollars and divide by 100, $2.52, right? So that's it. We show that this is correct. Well, in multiple choice, I cannot give you a question where I say show that. So if this ends up being in the exam, you will have to find this number, right? Or pick the one that's closest. So next question is this one. A 4-watt night light is plugged into 120 volt circuit and operates continuously for 1 year. Okay, I have a feeling we will have to do lots of conversions here, so this will take several minutes. So it's broken down into parts for you, A, B, C. So what I will do is I will just answer those questions individually. So the first one says the current, how much current does it draw? So to find current, what was current? Current was charge per time, but that's not useful here, right? Another one is Ohm's law, but V equals IR, but I don't know resistance, right? So I cannot, can you think of an equation that has current in it, but also power? So maybe it's this one, power equals current times voltage, the one we just covered, right? So we have 3 equations which have current in it. So at the exam, you have to make a decision, educated guess which one you have to use. Probably you have to use the one that contains the variables that are given. So voltage is given and power is given, power and voltage. Because of that, I choose this equation here. So let's do it. Current from here equals divide each side by voltage. We will get power divided by voltage. So power is 4 watts and divide by voltage 120 volts. And I will end up having an awkward number. It's not divisible, it will be 1/30. But yeah, let's see what that is. 0.303 recurring. So something like 0.033 amps. Okay. Next question is find the resistance of this lamp. So this was A. Let me do a different color. So to find resistance, again, remember we said we know 3 equations that contains current. So I'm going to go for the second equation, the one that's Ohm's law, right? V equals IR, because that's the one that has current and resistance at the same time. So resistance is what we want to find. Solve it for R, which is voltage divided by current. And you can just look up this formula if you like, instead of using the first formula. So this formula will help me find resistance because I know voltage is 120 volts and current is this 0.003 recurring. So 3, 3, 3, and so on. And we will get 3,600 to nearest two significant figures, let's say. And this will be in ohms. And next question, let's choose different color. C, the energy consumed in a year. So we know power, and we know that time is 1 year. So first thing I guess we have to do is time needs to be in hours, right? So in hours, time would be, because later we are given cost in kilowatt hours in part D, and we will have to find total cost. So that's why. So time needs to be in hours. So 1 year, how many days is 1 year? 1 year is 365 days, and each day is 24 hours. So 365 times 24 hours. As exam, don't worry too much. I will not give you, definitely not give you so many conversions, because time is a limit. Time is limited. So I will maybe give you a number of hours, or if I do give you conversions, it would be easy ones. So then that would give me 365 times by 24. I get 8,760 hours. So now time is in hours. We are good. So to find energy was power times time. And power was, what was it, 4 watts. We could convert it to kilowatts. For later, we will need it because we will end up with the right units. So 0.04 kilowatts, because we divide by 1,000. And time is in hours, so we will end up with kilowatt hours. So let's times it by that. So we have 35.04 kilowatt hours. So this is energy. Now, how do we find? I'm afraid I have to erase some of it. I will just erase this part. So we got in previous one, all of that equal to approximately 35 kilowatt hours. And in part D, we want to find total cost. So we know how much energy we consume, and we know energy is cost per unit of energy, cost per kilowatt hour, and we know we use 35 kilowatt hours. So if 1 kilowatt hour costs 15 cents, how many of such 15 cents do I have to pay? 35 of those, right? So total cost would be 35 of those, 35 kilowatt hours consumed multiplied by cost per each kilowatt hour, and I will end up cents, and I will do it in green, no, in red. So that would be 35 times 15, 525 cents, but we need it in dollars, so it will be divided by 100, $5.25. And this is what we wanted to show. So those kind of questions, they are involved, but it's always, once you know how to do it, it shouldn't be too bad. There is 2 more which are relatively easier. So an electrical device, by the way, electric and electrical are used interchangeably for electrical power or electric power, for example. So if you know which one is more correct, you can let me know, but I have seen both of them used in different books, so I will also use them as interchangeably as well. So an electrical device draws half amps of current from 120 volts, so that's given, and we need to find power. So power, this is easy because I'm just using a formula, is current times voltage, and current is half, voltage is 120. I would strongly recommend to pause it before you start doing those questions, and do it yourself, and then you can check your work. That's how you learn better. Because if you just see someone else doing it and you agree with what they did, it's not teaching you something new. So in this question, you have two toys that operate at different power ratings, and you need to figure out which one costs more for 2 hours, to operate them for 2 hours. So the first one, was the first toy. Power of that would be current times voltage, right? So 0.3 times 120, which would be 36 watts. The second toy would have power equal to 50, oh, it's already given, 50 watts. So they both are on for 1 hour. Okay, 1 hour. So total energy would be 36 watts hour, or kilowatt hour as well. We could convert it if you want. And total energy, so this is energy. Because energy is power times time, so I multiplied power by 1 hour. So here, total energy consumed in 1 hour would be power multiplied by 1 hour, or it will be 1 times 50 is 50 watts hour. Watts hours would be units of energy. And now I forgot to give you here cost of one. Cost is per kilowatt hour is, let's say, 10 cents. 10 cents per kilowatt hour. So if each kilowatt hour is 10 cents, how many kilowatt hours that would be? That would be divided by 1,000 to convert it to kilowatt hours. So it would be 0.036 kilowatt hours. And this one, how many kilowatt hours? 0. Divided by 1,000 watt hours per hour. So how much more does it cost? So let's find total cost for the first one first. So cost will be number of kilowatt hours multiplied by cost per kilowatt hour. So 10 times that. Multiplied by 10 cents per kilowatt hour. And that will give me kilowatt hours cancel. So 0.36 cents. So it's a really tiny amount of money that you have to pay to operate it for 1 hour, because it's just 1 hour. And the second one, let's do it in black. Again, cost would be equal to 0.05 times by 10 cents per kilowatt hour. Kilowatt hours cancel, so it's 0.5 cents or 0.50. And so how much more does it cost to operate? So how much more does it cost to operate the first one versus the second one? So it would be 50 cents cost of second one minus the first one, right? 36 cents. Oh, 0.14 cents, sorry. It was 0.5 cents. So 0.50 cents, really. 0.5 is the same as 0.50. So you can use calculator here and find the difference in cost. So it's a bit cheaper to operate this first one. Next, I want to talk about safety fuses. So what is a safety fuse? It looks something like that. We have a diagram here. And what it does is it protects the device from burning or damaging. Suppose we have a circuit like that. This is where you plug in this device, and the mains carries current. We get this hot wire here carrying the current to the device. So I don't know, something here. It could be anything really. Let's say microwave oven. Or any, even it has to be something, a computer, for example, and it carries the current back like that, right? So this is what's happening really. When we connect a device, we have this wire, which is really two thin wires that are plugged in like that. So this current flows that way, and then it flows that way. So we have a closed circuit here. So hot wire carries current to the device, and then it goes back to this one here, the ground one. So what is fuse? We put a fuse like that somewhere inside the device, but it is in series with this device. So current flows, the same current flows through the fuse as the device. And this fuse has a really fragile, let me do it in green, this wire here that is really, really thin. Okay, so this wire inside the fuse is really thin. And it's designed, well, how thin, it depends on how much current we want it to let through. So if we want to protect this device here from, let's say, 10 amps of current, suppose anything 10 amperes or more would break, damage this device. Because too much current, you know that it can overheat objects or cause different damages. So to protect it from that, we put a 10 amps fuse. And what will happen is that this current that flows through that is too high for that wire. If it's 10 amps or more, this wire will just melt because it's so thin, because it gets hot and eventually melts. So we would have something like that, a break in this fuse. And this means that now this circuit is open circuit. It's not a closed circuit anymore because current cannot go through that anymore. So no current would flow. So this fuse, in fact, protects this device from damaging by high currents. So it breaks itself instead of the device, really. And we have different types of fuses. And if we are talking about homes, for example, then you might want to install circuit breaker then fuse, and broken fuse needs to be replaced. But first you have to figure out why it was damaged, why the current was high. So there could be different reasons why the current was high. For example, what sometimes can happen is if the wires are too long, you know that too old, I mean, you know that those wires are insulated, right? So because you never see those wires inside, so that they don't come in contact. And if this insulation breaks, then we have two wires touching each other like that. And if that happens, then you know how we talked about how current always chooses the easy path of least resistance. The current would not flow this way through the device and back, but it would instead find a shortcut. I'm showing it in blue here, like that. And you know that voltage equals current times resistance, right? So let's think what happens here. If voltage is the same, 120 volts, because that's what we have in the mains, and let's say resistance is negligible because there is nothing connected to this circuit really. It's just wire with really tiny resistance. If there was lots of things connected, then resistance would be big and current would be small. But because resistance is so small, because the wire almost doesn't have a resistance, negligible resistance, then the current could be really, really high. And this really, really high current could be dangerous. It could melt things, heat them up. So because of that, high currents could cause fires. And to protect homes from fires, what you want to do is, whenever the current is too high, you want to put something, a circuit breaker there, or a fuse, I guess, which has high amperage. And then it would just stop current from flowing. So it's there's different ways you could make it work, I guess. We didn't cover that yet, but you could use metallic strips that bends when it's hot. So lots of ways to control it, but the idea is the same. You want current to stop current from flowing when it's too high. So somehow circuit detects really high currents and the circuit breaks. Either fuse breaks or switch is activated and it switches off the current.